Hello, Chinthaka.
How are we?
So, we started with some pre-photographs or pictures initially.
Right.
And one we identified this was a resistive-based position sensor
Yes.
or linear position sensor,
Mhm.
but a resistive-based one.
Correct.
The second figure was this. And then you were saying that this is I forgot. What did you say? Some inductive based one, no?
Yeah, I was asking you why there are some coils. I see some coils in there.
Oh, that is spring.
That's a spring.
This one, no?
Yeah,
This is spring.
this is spring. Okay.
But you said this is inductive based.
Yeah,
Maybe you guessed it from.
yeah. I just thought maybe.
Yeah.
Yeah.
But when you say inductive based, what it means? I'm not sure.
I mean, if you talk about inductive, thinking about, I don't know, transformers
Yeah.
or magnetic fields.
At least there will be some coil.
Definitely.
Maybe there is some core. That's what you meant by
Yes, yes.
transformer.
Yes.
Hmm?
Yes. These are the, basics,
Hmm.
right? If you talk about inductance, that's the first thing that comes to your mind. Some coil, as you said, some core.
Uh-huh.
But then how?
So somehow we have to figure out what is there inside.
But we are still trying to measure displacement.
Right.
But now we are thinking about
a different mechanism.
different mechanism. Okay.
I mean, we see this fixed member and mobile member, etc.
Yeah. So that part looks the same, right?
Yeah.
And also it's kind of a long straight kind of rod.
Correct.
But the thing is, you said previously that you looked inside.
Yeah.
Now my question to you is, have you looked inside?
Did I
Have you
look
looked
inside?
inside? Please,
course I did.
otherwise.
Of course, I did that. But still, maybe you can question me a little bit more.
Right.
Um,
So you're saying it's still the same. You have a fixed member and a movable
member. And you also said coil. Maybe I'll start with a coil.
Okay.
Maybe I'll draw a coil on a former or a bobbin. I mean, like if you have a tube.
Right.
And on which let's take cross-section view. Let's say there is a tube.
Right.
And on which I make some winding.
Just with some wire.
Yeah, just with some insulated wire.
Right.
Let's say something like this.
Okay.
Maybe. So it starts from here, ends at here.
Right.
And let's say there are n number of turns.
Okay.
My drawing is not proper, but let's say it's uniformly wound. Right? And suppose if I measure the inductance between these two terminals, let's say A and B, using some meter.
Okay.
There is something called LCR meter.
Yes.
You can measure inductance L or resistance R or capacitance C. Let's say I measured L. What should I get? Value? We don't know. Or what we know is it will be a function of the number of turns.
For sure.
Maybe the length of this winding.
Yes.
Let's say L.
So when you say length of the winding, right?
Yes.
Not of the bobbin.
It's a winding.
It's a winding.
Yeah.
Yes.
I mean, for example, if the bobbin is this much.
Yeah.
Which is usually made of non-magnetic material. Let's say PVC tube, for example. Right. That doesn't count the portion for which there is a winding.
Right. That's the length.
That is the length.
Okay.
Then
maybe the area?
The cross-section
area.
So what you're saying is, I mean, if you take a cross-section, of course it's not great, but I will try. The tube cross section will be something
Pretty
like
much,
this.
because you're winding it around.
Yeah.
Yeah.
And the winding is surrounding it. So approximately this cross section area. Okay. Okay. So that's another factor. What else?
Mm,
In fact, we see only that much in this.
yes. Number of turns.
So it will be a function of all this.
Yes. The inductance.
And it's air. Rest of the space is air.
Yes.
And I think air has got some permeability mu 0.
I think. But, this I remember.
Yeah.
4 pi.
4 pi into 10 power minus 7.
7. Yes.
Correct. So it will be a function of all this.
Yes. Inductance.
Inductance.
Yes.
And if I replace this air inside with some other magnetic material,
Okay.
which has got some relative permeability,
Okay.
let's say mu r,
Okay.
then finally this inductance will be a function of all this. I think there is a standard formula which all of us know. This L will be approximately mu 0 mu r n square A by L.
You have a good memory, Boby.
I hope it's correct. But at least what I remember is these are the factors that decide this value of
The main parameters for inductance.
Yes. And what we don't see is, I mean, to measure this inductance, of course, that LCR meter will be applying some voltage, sending some current,
Yes.
finding out the impedance or reactance. From there, calculate the inductance.
Correct. Yes.
It's not a function of the current flowing through it.
No.
It's not a function of the voltage that you applied.
Yes. But to measure, you need
Yes.
some current to flow
Yes,
through it.
we will have to do that.
Yes.
So it's only a function of the physical parameters.
Okay.
The size of it, the number of turns of it, the material, the magnetic material. If it's a ferromagnetic material that is used, then it's relative permeability.
Yes.
Permeability of air. Only those physical parameters.
Right.
Okay. This is now if our objective is to get some displacement.
Yes.
Measure the displacement.
Yes. Using this principle.
Yes.
I'm struggling
And we
to-
started with saying transformer or a coil or
Yeah.
but how we can relate it to, or how to what. In the case of resistance, we said is rho L by A. We will change L straightforward.
Yeah, that was
we said.
pretty straightforward. Yeah.
Here, I cannot unwind and wind. We can do, but that's not the best way.
But somehow
There is no wiper here.
but somehow the displacement must be related to, right, a function of
Yes.
inductance, right?
Yes.
Somehow.
Yes. Now, other than inductance, we may also know if you have two coils.
Okay.
Suppose if I have one more of them nearby, let's say there are two coils next to each other.
Okay.
And then sometimes we see some dots like this. In the symbolic representation.
Right.
If you have just one inductor like this, we show this. If I have one more of this nearby in the physical vicinity,
Yes.
sometimes we show some dots. And sometimes people also mark some M there.
I know what you're getting at.
Yeah. So what you meant is, this is the mutual inductance. Now, my question is, it's difficult to show here. Suppose I move this coil little bit far from this coil. Let's say I moved couple of mm. Will something happen to this mutual inductance?
I would say so. I'd say it decreases.
Yeah.
Right.
So in the case of transformer, we used to refer this term coupling factor or
right.
So the M will change.
Yes.
So maybe we can make use of that.
Well, we have a fixed member and a
Yeah.
movable member.
Correct.
Can we?
So probably if you have two coils like this,
Yes.
And then if you can somehow measure that mutual inductance,
Mhm.
mutual inductance will be a function of the displacement between these two coils.
Yes.
So if maybe one is on the movable part and one is on the fixed part, this could be one way to
measure the displacement.
Get a inductance or mutual inductance
Yes.
as a function of displacement.
Yes. Because you're moving one, the other one's fixed.
Correct.
Okay.
But I think there are some practical problems. I need to have wires connected to, these terminals to measure. Suppose, let's say this is a movable one.
Mhm.
When I move the plunger, these wires will also be moving.
That's true.
Of course, how many times you can bend this wires?
Right.
So the lifespan will be affected.
Especially if you're using it in an industrial setting.
Correct.
Right? It will just break after a few rounds.
So that will be a problem. So preferably, I would avoid any wire connection from a moving part.
Okay. What about range? Do you think mutual inductance will limit the range of the displacement?
Yeah, of course. I said I moved couple of mm. Suppose I move 30 centimeter.
Yeah.
Depending on the coil size.
Right.
Let's say this is only this diameter what we are talking. Let's say it's only 1 centimeter.
Okay.
And if I move the coil maybe 10 centimeter away, you don't see anything.
Yeah. So your range will be limited as well.
Yeah.
If you use this method.
Correct.
Because from the photo that you showed before, they are pretty thin rods, right?
Correct.
So
and it's a bit lengthy. From the aspect ratio,
right.
It feels that way.
So yeah.
Mm-hmm. So we prefer not to have a coil on the plunger. That we are clear.
Right.
Now what to do? So this, I was thinking we are close to a solution. Do you want to change anything else here?
Well, if you have let's say something magnetized, right, going in and out, will that induce?
So what you're saying is here we talked about this mu r.
Mu r.
Okay, so
change in magnetic field. Moving. You said one's moving. It's moving up and out. Wouldn't that induce some voltage or something on the coil?
Okay. Voltage, I don't know.
Some current, which then you can measure as voltage.
So for that, it has to be a magnet.
Yes, that's what I'm saying. I'm saying if you have a magnet,
right?
And if you move it, so then your magnetic field is changing. If you're moving it in and out,
then that will be function of the velocity, I think.
True. That is true. Yeah.
There, yes. Because if I move very slowly,
yes,
the voltage will be too small to measure.
Because your change in magnetic field will be proportional.
Correct.
So I'm talking about a magnet.
Yeah. Yes. So I would prefer,
again, not practical and also not ideal, right?
Correct.
Because then again, like the previous example with the capacitor, right?
Yeah.
You don't want the capacitance.
Correct.
Now here we are adding another variable.
Correct.
Speed at which it moves.
Yeah.
We don't want that.
Yeah. Because we are measuring only, aiming to measure only the displacement.
Exactly. But now if that also depends on the speed, that's a problem.
But instead of a magnet, if it's a ferromagnetic material, not magnetized,
yes,
it has some permeability.
Yes.
Relative permeability of, let's say, 1000 or even higher, easily available. And if let's say this, the tube that we have drawn here is empty.
Yes.
And then we introduced a ferromagnetic material inside.
Okay.
which is free to move inside.
Okay.
That's what you're saying.
Yes.
Okay. So since we said L is like this, and I mean, this is, let's say, initial position, but then I think that's a bit difficult to draw. Let's say some other position is like this.
Okay.
Then we have some portion of the coil exposed to this material. Some other portion is not exposed to.
Right.
So definitely
There will be some change.
there will be a change.
Okay, I see. I see what we are getting at now. So this is your movable member now.
This is my movable member. Now, anyway, this is moved out of this.
Okay.
As per this drawing. So I can maybe, here I have two windings, no?
Yes.
So the second winding can be close to it, such that when it comes out, it can enter into the other one, which is also possible.
Right.
So that way, I will have one of the inductance increasing and the other one decreasing. So, there we could make use of this change in the inductance itself.
Yes. Correct, by moving.
Yeah, yeah. So when the core is moved, there is one inductance increasing, other one decreasing. So this could be we could make use of that.
Yes.
To get a displacement output.
Right.